Hello and welcome to lecture 53 of analog integrated circuit design. We have studied a number of circuit blocks in this course so far, and in all of those cases we have assumed that there are bias currents and voltages available. In the next couple of lectures, what we will do is to see suitable ways of generating those bias currents and bias voltages. Okay. Now, first we will assume that if we want a constant current source, it is available. Now, one way to do that is if we have a constant voltage, we basically convert the voltage to a current using a circuit of this sort. I will not explain how to come about this one, but this is a very simple circuit. So, this circuit is very simple. In negative feedback, the voltage at the source of the MOS transistor equals Vref. So, the current through this is Vref divided by R. Okay. Now, if Vref is constant and R is constant, this current will be constant. Now, how to get a constant Vref we will not discuss now, we will discuss it later, and this constant current can be mirrored to a number of places using current mirrors. Okay. If we have MOS current mirrors, we can replicate it as many times as we want, and these will push current, and if we want to pull current, we can further mirror this using an NMOS transistor. Okay. So, this is how to generate a constant current source and we can replicate it. What it needs is a constant voltage source, we will later see how to do that. When I say constant, what I mean is it must be constant with variations of temperature and supply voltage and process and so on. Okay. So, the supply voltage will vary by some amount. If you for instance use a battery, the battery voltage will be high in the beginning, then drop down to some constant value and then becomes low as it gets discharged. Also, if you use a voltage regulator as well, there will be some tolerance in the output voltage, and temperature of course can vary based on the ambient temperature and the power dissipated on the chip. And finally, there are process variations. So, that means that the component parameters are different in different process corners. Now, the next thing is that one of the uses of a current source is to bias a differential pair or a transistor. Okay. Now, for instance, if we bias a differential pair like this with I naught, the GM, the transconductance of this differential pair depends on I naught. Okay. Now, one of the interesting things is to design this in a way that keeps the GM constant. So, what I mean is if I naught is constant over temperature, what happens is that GM, which is square root 2 times I naught by 2 for this case divided by mu Cox W by L, this does vary with temperature. This is because this reduces as temperature increases. Okay. So, if you do this, what happens is at low temperatures you get high GM and at high temperatures you get low GM. Now, this may not be desirable. For instance, in an op amp, the unity gain frequency depends on the transconductance of the first stage, and it may be beneficial to keep that constant over temperature. Okay. So, one of the things is to be able to design a current source I naught such that the GM of the MOS transistor will be constant over temperature variations. Okay. So, we will see how to do this, and for this first we will look at a differential pair made using bipolar transistor, because that makes it simpler to explain, and after that we will see that exactly the same circuit works for MOS transistors as well. Now, Gm of each of these transistors is the collector current divided by the thermal voltage. Okay. Therefore, to keep Gm constant, I naught must be directly proportional to the absolute temperature. Okay. This thermal voltage is kT by Q, which is proportional to absolute temperature. So, if the bias current is also proportional to absolute temperature, the ratio will be independent of temperature. Okay. Now, how do we get a quantity that is proportional to absolute temperature? Again, this quantity Vt gives us the clue. This quantity, the thermal voltage, is kT by Q, and this of course is proportional to the absolute temperature. So, we can use this to try and come up with something that is proportional to the absolute temperature. We do know that the base emitter voltage of a bipolar transistor or the forward bias voltage of a diode is Vt times natural logarithm of the collector current divided by the saturation current. So, in this we have a term that is proportional to the absolute temperature. Okay. So, let us say that I have a bipolar transistor biased with a current I naught, then this VBE will be Vt times logarithm of I naught by Is. Okay. Now, this part is proportional to the absolute temperature, but this also depends on temperature. Okay. In fact, it depends very strongly on temperature, as we will see later. So, this by itself is not useful, but if we notice this, we have Vt times log of something. Now, if we pass the same current through another transistor, so let us say the area of the first transistor is 1 Q1 and the area of the second transistor is some n, okay, n times that of the first one. Basically, we do this so that the saturation current of this is different, it will be n times that of the first transistor. Okay. So, the VB1 will be Vt ln I0 by Is and VB2 would be Vt natural logarithm I naught divided by n times Is, because the saturation current of Q2 is n times the saturation current of Q1. Okay. Now, if we take the difference between the two base emitter voltages, it turns out that we will get exactly what we want. Okay. So, VB1 is Vt log I naught by Is, VB2 is Vt log I naught by NIS, and the difference VB1 minus VB2 would be Vt natural logarithm of n, which is a constant, that is simply the ratio between Q1 and Q2. As usual, for accurate realization of ratios, we will make Q2 n units of Q1. Okay. So, if you use 1 unit for Q1, maybe we can use 8 units for Q2. So, this n will be 8 and accurately realized. Okay. So, now we have a voltage which is proportional to absolute temperature, and if this voltage appears across a resistor which is constant, then the current will also be proportional to the absolute temperature. Okay. Now, how do we do that? VB1 minus VB2 must appear across a resistor, okay, and obviously the resistor must have 0 temperature coefficient, okay, that is it must be independent of temperature. That of course will not be realizable exactly, but we should try and have a resistor which has a very low temperature coefficient. Now, how do we do this? So, we have VB1 over there and VB2. If I connect a resistor here and the voltage here happens to be VB1, then clearly the current in this will be VB1 minus VB2 divided by R, which is Vt by R times natural logarithm of n. Okay. So, the goal is to have VB1 over here. Okay. So, one of the ways of doing this is that we drive a current into this and continuously adjust the current until the voltage here becomes exactly VBE1. Okay. So, the reason we do this is that finally, we have to be able to replicate this current as well. So, now if we have adjusted this current source by some means meaning we have to adjust the gate voltage of this until the current in this is such that the voltage here becomes VBE1, then we can also make multiple copies of this current by copying the source gate voltage of this transistor onto other identical transistors. Okay. So, and how do we do this? We compare Vx with VBE1, and if Vx is different from VBE1 we have to adjust VGP. Okay. So, we integrate the difference between the two, say using an op amp, and drive VGP. Okay. And we have to do it until Vx becomes equal to VBE1, and we have to adjust the signs of this op amp so that the circuit is in negative feedback. Okay. So, with this arrangement that is possible, we have done this for many things. Now, the other thing is that the difference between these two voltages VBE1 and VBE2 will be equal to Vt ln n if the currents in the two transistors are the same. Okay. I have not shown how to bias the transistor Q1, but the current in this has to be exactly the same as that. Now, the current in this has been adjusted to the right value if everything is working properly. Okay. So, we can replicate that into another PMOS transistor and bias it. Okay. Now, M1 and M2 are identical. So, the currents in these two transistors will be exactly identical, and also because the gate of this is driven by integrating the difference between Vx and VBE1, Vx will be equal to VBE1. So, finally, when the circuit reaches steady state, the current in this equals VBE1 minus VBE2 by R, which is Vt by R times ln n. Okay. Now, this has a certain snake swallowing its own tail quality to it, that is we bias the second branch using the first branch, and then the first branch itself is biased by replicating the current from the second branch onto the first branch. Okay. So, this kind of circuits are known as self biased circuits. As you see, there is no current source here, no other current source that biases up the circuit. If the circuit reaches the right steady state, the current will be equal to Vt by R times ln n in both the branches. Okay. Now, one of the problems with these circuits, and in fact this happens repeatedly with bias circuits, is that it has two possible states. Now, one possible state is what I just showed you, the other state is when both the currents are 0. If both currents are 0, VBE1 and VBE2 will both be 0 and the gate voltage VGP can be VDD. Okay. This is possible. Now, if that is possible, all transistors are off and the circuit will be in steady state. Clearly, that is not the operating point that you would like to have. You would like to have the operating point where the currents in both are non-zero. If it is non-zero, then the only possibility is for them to be Vt by R times ln n. Okay. So, what is done in these circuits is to make sure that when you switch on the circuit it starts up properly, you provide a starting current. Okay. That is, if some voltage is stuck to VDD or ground, you make sure that it increases above that. Once it increases above that, the circuit will reach the correct steady state, and at that point the extra current should become 0 or negligible. Okay. So, one way to do that is, so let us say we find that this voltage is at VDD and these voltages are at 0. Now, if we pull down the gate voltage of these transistors, what happens is M1 and M2 will carry some current and these voltages will be lifted above ground. Once it is lifted above ground, the negative feedback comes into picture and the entire circuit reaches the operating point. Okay. There are a couple of ways to do this. In some circuits a pulse is available at startup, using that this voltage can be pulled down momentarily. Now, we will assume that no such pulse is available. In that case, what you do is, you have to pull a current using this NMOS transistor, and if you make this gate voltage high, it will pull the current. So, what can be done is a circuit of this sort. Okay. Now, this PMOS transistor will pull the gate of the NMOS transistor high if its gate is at 0. Okay. Now, we saw that if the operating point is 0, then the base emitter voltage here will be 0, VBE1 or VBE2. So, we can take this signal. So, if this happens to be 0 at startup, this PMOS transistor will pull the gate of the NMOS transistor up. Let me call this MP and MN. The MN's gate will be pulled up and this will draw a current, and once this draws a current, this VGP will be pulled down and these two will push currents into the bipolar transistors and this voltage will be lifted up. Okay. Now, what must also happen is that if this voltage is lifted up to a sufficiently high value, then this Mn should not be drawing any current. Okay. And that can be ensured by connecting it up like that. Okay. Essentially, we have a CMOS inverter structure here. So, if this voltage reaches a sufficiently high value, which is about 0.7 volts or so, this transistor tends to pull this node down and deactivate Mn. Okay. Now, of course, all these things have to be adjusted by simulation, the sizes of all these things. This Mn will be rather weak, that is, it will carry a small current to begin with, and that current should become even smaller when this voltage goes to the appropriate value. Okay. And let me call this Mn dash. The MP and Mn dash should be sized such that when this reaches the appropriate value over all process corners, the current in Mn becomes negligible. Okay. So, this is an example of what is known as a startup circuit. It provides some bias current at startup. This is to ensure that you do not get stuck with the 0 operating point and must drop out of the picture, that is, must carry negligible current after startup. Okay. So, that is the role of a startup circuit. Lot of these reference circuits will be self biased, because you are using the reference to generate some bias current or bias voltages, and that is used in the reference itself, and such circuits need this startup. There are more elaborate kinds of startup that you can think of as well, and you can also find them in the literature. So, what we have here is a circuit which provides a bias current which is proportional to the absolute temperature. Okay. And if you bias a bipolar transistor differential pair or the bipolar transistor using this, its transconductance will be constant with temperature. So, what do? We can replicate these currents any number of times we want. Okay. And I have used both bipolar and MOS transistors here. Our dominant technology is MOS, but if necessary, these current sources can also be realized using only bipolar transistors. Okay. And this op amp also is realized using either CMOS or bipolar, depending on the process that you have. Now, one of the things is that the offset of this should be small, because ideally these two voltages are made equal by the action of the negative feedback, but in reality there will be a difference between them equal to the offset. Okay. So, that will cause an error in the current. So, you would like the offset to be as small as possible, so that the error also is as small as possible. Okay. Now, one of the other things to be considered is that unlike in many other circuits, in this circuit the op amp has feedback to both terminals, okay, both of the input terminals. So, we have to figure out the signs of the op amp, so that the overall action is of negative feedback, okay, and that can be done very easily just as usual by breaking the loop and applying a test voltage and so on. I have chosen to break the loop at the output of the op amp, and I will apply a test voltage V test. I will assume that these two are identical, of course, M1 and M2. So, the incremental currents in both of them will be V test times GM1, and the incremental voltage here will be V test times GM1 times the impedance looking down, and that is nothing but 1 over Gm of the transistor Q1. Okay. So, the voltage here at this point will have minus Gm1 by Gm_Q1 times V test, and similarly here we have R, and the impedance looking down there is 1 over Gm_Q2. The voltage that appears here is minus V test Gm1 1 over Gm_Q2 plus R. Okay. Now, depending on which one is greater, we have to assign the signs appropriately, okay, and that depends on the relative values of Gm_Q1 and Gm_Q2, but these two transistors are biased at the same current. Okay. So, that means that Gm_Q2 equals Gm_Q1. The Gm of a bipolar transistor depends only on the collector current, and the expression is IC by Vt for both. So, you can clearly see that this Gm1 by Gm_Q1 is some number, and here we have Gm1 times 1 over Gm_Q1 plus R. So, the gain from V test to this point is more negative than the gain from V test to that point. Okay. So, if you make the signs of the op amp like this, then the voltage here would be V test times Gm1 by Gm_Q1 minus Gm1 1 over Gm_Q2 plus R times the gain of the op amp, and because the two bipolar transistor Gms are equal to each other, this part will cancel out with that, and we will be left with minus V test A naught Gm1 R, okay, implying that there is negative feedback with this particular configuration of the op amp. Okay. So, this is something also that happens repeatedly with bias circuits. You may have op amps with feedback to both the inputs. That is very simple to analyze. All you have to do is to again break the loop appropriately and look at the small signal gain by after breaking the loop, and make sure that the loop gain is negative. Okay. So, the circuit that we have here has a current that is proportional to absolute temperature PTAT. So, this is many times called a PTAT cell. Okay. So, this part of the circuit is a PTAT cell. Okay. So, this is a way of generating a current that will make sure that the Gm of a bipolar transistor will be constant with temperature. Okay. Now, what can we do with MOS transistors? It turns out that exactly the same circuit will work with MOS transistors as well. The expressions are different for the current in MOS transistor and current in bipolar transistor. Now, even for MOS transistors in strong inversion saturation region, exactly the same principle works. Okay. Let us say this has a certain W by L and this has n times W by L. Okay. And we will assume that it is operating at an operating point which is different from 0. This is VGS2, this is VGS1 and the current is VGS1 minus VGS2 divided by R. Okay. Now, what is VGS1? That is Vt threshold voltage plus square root of 2I, whatever I is flowing here, let me call it maybe ID, 2ID by mu n Cox W by L, and VGS2 is the same threshold voltage plus square root of 2 times ID by mu n Cox n times W by L. We also saw that ID equals the difference between these two voltages divided by R. Okay. So, ID comes out to be square root of 2 ID by mu n Cox W by L 1 minus 1 over square root of n. The first term comes from VGS1, the second term from VGS2 times 1 by R. And if you solve for this, ID you can easily see is two by mu n Cox W by L 1 by R square 1 minus 1 over square root of n whole square. Okay. So, you can adjust n to be let us say 4 or something and then you will get some number over here. Now, the point is that if you bias a MOS transistor using that, by the way here we are talking about an NMOS transistor because this VGS difference that we have taken with the NMOS transistor. With the PMOS transistors we will have mu p's here and it will be different. NMOS transistor biased at ID its GM will be square root of 2 ID mu n Cox and I will say W1 by L1, okay, to distinguish it from other transistors. And what is ID? We know that square root ID equals the square root of this quantity, which is okay. So, GM1 will be the mu n Cox will go away, that is the important part here. Assuming as before that R is independent of temperature, you see that this GM1 is independent of temperature. It is related to ratio of aspect ratios that will be independent of temperature, the transistors will be well matched, and this number which again depends only on matching, n is the ratio of the aspect ratios of two transistors used in this cell. Okay. It turns out that exactly the same circuit that works to establish a constant GM in bipolar transistors also works for MOS transistors. Okay. Now, it is assumed that the MOS transistors are operated in strong inversion saturation. Okay. Now, if the MOS transistors are in a weak inversion, that is subthreshold region, then the MOS transistor behaves the same as bipolar transistor. It will have an exponential IV relationship and then also it works. Okay. So, this circuit also works for MOS transistors, but there is a slight problem with this. Now, anything else that we want to bias, we can also replicate these currents and use it as many times as we want, and if we want to pull currents, we can further mirror it with an NMOS transistor. Okay. But one of the problems is, so let us say I want to bias a differential pair with this kind of a current. Okay. I can do scaling as well. The currents in these do not have to be exactly the same as this, it can be a scaled version of that. For that I can use scaling in the current mirrors. Okay. Now, nominally these transistors will have exactly the same characteristics as those transistors and everything works the same. Okay. But in reality what happens is that there will be body effect in this and there is no body effect in that and so on. Okay. You will see that the GM of this will be slightly different from the GM of this one and the tracking will not be perfect. Okay. So, that is one of the issues with this one. Also, we derived these relationships using square law, that is the transistors are in strong inversion saturation and so on. We also know that as we go to shorter and shorter technologies, the transistors do not exactly follow square law. So, any deviations from square law will also cause deviations from this behavior, that is the GM will not be proportional to 1 over R as was predicted by the expressions we derived. Okay. So, there is an alternative circuit which is more fundamentally sound and that is then that utilizes just the definition of GM. And what is GM after all? If you apply a small signal to a differential pair, the current will be GM times the small signal input. Okay. So, in those cases where you want to stabilize the transconductance of a differential pair, you can use a better circuit than this which will keep the GMs constant. Okay. And that will be independent of square law and independent of whether they are in strong inversion or not, and also it turns out it is not so affected by body effect, that is you make sure that the transistors that you use in the biasing cell have the same body effect as the transistors that you use as a differential pair. Okay. Now, how do we go about doing that? So, let us say the differential pair is biased with a certain current to I1, that is the tail current. Okay. In quiescent condition, each of these currents will be equal to I1, and if an increment Vd is applied, then the current in the left side will be I1 plus Gm by 2 Vd, and here it will be I1 minus Gm by 2 times Vd. Okay. And let us say that I generate a Vd by passing a reference current Iref. Okay. I have not shown how the complete circuit yet, but Iref through R. So, this Vd will be simply equal to Iref times R. Okay. And let me call these two drain currents IA and IB. IA is I1 plus Gm by 2 times Vd, IB is I1 minus Gm by 2 times Vd, and Vd itself is I ref times some R, and again this R is assumed to be constant with temperature. Okay. So, these currents will be nothing but I1 plus Gm by 2 I ref R, and this will be I1 minus Gm by 2 I ref R. Okay. Now, if you consider Ia minus Ib, that is GMR times I ref, and if you make Ia minus Ib equal to I ref, that means that GMR is 1 or GM will be 1 by R. Okay. Now, what it means is that I have to change the transconductance of the differential pair until this GMR times I ref, which is the output differential current of the transconductor, equals the reference current I ref. In those conditions, obviously Gm times R is 1 or Gm will be equal to 1 by R, and as we have said, R is constant with temperature. So, Gm also will be constant with temperature. And as you noticed, in this case we have not used anything of the particular characteristics of the MOS transistor. Okay. We have simply assumed that it is operating in a small signal regime, so that the differential output current can be written as Gm times the differential input voltage I ref times R. Okay. So, as long as that is valid, this circuit will work. Now, we have to what we have to do is to complete the arrangement, so that the transconductance of the differential pair is varied until its output differential current becomes equal to I ref. Okay. We have to vary Gm, and how do we vary Gm? By varying the tail current to I1, which means I have to vary to I1, which in turn means that I have to vary this Vg naught. Until Ia minus Ib equals I ref. Okay. So, we will see how to do that. I have to arrange it such that if Ia minus Ib is more than I ref, I have to reduce Gm, which means I have to reduce Vg 0, and similarly if Ia minus Ib is less than I ref, I have to increase Gm and increase Vg 0. Okay. In other words, this same condition written differently. So, we have to be able to take this term here Ia minus Ib minus I ref. Okay. So, let us say I ref is provided by some MOS transistor. I will call this MR1. Okay. And anything else connected with the same source gate voltage will also provide the same current I ref. Okay. So, what I will do is I will first fold these currents. The reason I have to do that is because finally I have to provide a control to the NMOS gate. So, I will use a folded cascode structure. and these bias currents will be 2I1, okay. It will be the same as this one, and by using appropriate current mirroring arrangements I can make sure that the current here is the same as the current there, okay. All I have to do is to bias this gate appropriately. So then what happens at this point, I will get 2I1 minus IA, and here I will get 2I1 minus IB, okay. Now using another current mirror arrangement, imagine a parasitic capacitance here, so that we can see which way the voltages go. If I use another current mirror like this, what happens is here I get this current will be 2I1 minus IB as well, it is simply the same as that current. So a current of minus IA plus IB tends to flow in this one, okay. Now what happens is this voltage will increase or decrease depending on whether this current is positive or negative. Now this is close to what we want, but not exactly the same. What we want is an extra term of IREF, okay. We want this voltage to increase or decrease based on IA minus IB minus IREF, and that is very easy to arrange. All I have to do is I have to add a current which is IREF, which means that I simply have to bias it from the same voltage as that one, okay. So here I will get 2I1 minus IA plus IREF, okay. So the current here also will be minus IA plus IB plus IREF. Now what happens if this term is more than 0, that is IA minus IB minus IREF is less than 0, then this voltage will go on increasing, okay. And similarly if this term is less than 0, this term will go on reducing, okay. And you see that is in exactly the direction that we wanted, okay. So you can go through the synthesis yourself and make sure that it is in the correct direction. So all I have to do is to connect it here. Now what happens, this voltage will reach a steady state, it will stop varying only if this term equals 0, that means that IA minus IB equals IREF, okay, and that is exactly the condition that we wanted, okay. So what this circuit does is to make sure that the GM of this differential pair, remember this is not working on the GM of just a transistor, but it is for the differential pair, equals one by R, okay. Now earlier I said that first of all this is not sensitive to whether the transistor is following square law, because we have not used that anywhere. All we have assumed is that this differential voltage Vd is small enough, so that the output current of this differential pair can be represented as something being linearly related to Vd, okay. So it has to be operating in the small signal regime, that is easy enough to arrange. Now the other thing is that finally what we will do is we will replicate this current 2I1 and maybe scale it and use it in another differential pair, okay. One of the problems with the earlier arrangement was that this transistor whose GM is stabilized to something inversely proportional to R are operating with 0 VSB, whereas these transistors are not operating with 0 VSB. So they are really operating with different body effects, whereas here I can make sure that the common mode input of this differential pair is the same as the common mode input of the differential pair I am using, okay. So this transistor and the actual transistor that I use will be suffering from the same body effect, or will be suffering from body effect to the same extent. So there will be no difference induced by body effect either. So this is a much more robust way of realizing a constant GM differential pair, that is a differential pair whose GM is constant over temperature, okay. There are just a couple of more details that we will fill in quickly. We need to know what we do with this node and also how to generate these sources. okay, because we do not want to be biasing with some other external sources. Again we use the principle of self biasing. Let me redraw this quickly. This is the differential pair whose GM is being stabilized. And this is the folded cascode arrangement. So, what we do is we use self biasing. Okay. So, that means that finally, when this current is 2 I1, this will be 2 I1 and these currents will also be 2 I1. And to this I have to add the current sources Iref. Now, it is possible to do it like this. Okay. That is, you make Iref also equal to I1. So, let us say this is 2x and this is 1x and this is 1x and so on. So, Iref can be made equal to I1, but one of the important things is that the current that is injected here and the current that is injected here should be matched very well. Okay. There cannot be any error between the two, because finally we are relying on this current being exactly Iref for the negative feedback to settle to the correct operating point. So, we may have to use accurate current sources here. So, it could be that you will use cascades. Okay. So, in this particular place you can use a cascade arrangement instead of a simple current mirror. Okay. So, all of the upper rails are VDD of course. So, here you use a cascade. The cascade bias can also be generated. We have discussed this earlier in a different context, but they can also be generated from some arrangement where this transistor has a much smaller aspect ratio than the other transistor. So, that this gate voltage is lower than that gate voltage, that is possible. And finally, we have to fix the voltage at this particular node, and that is fixed such that the common mode voltage of this differential pair is similar to the common mode voltage of the differential pair we are trying to bias. So, let me draw that. So, let me just show a representative differential pair. If this has W by L and this has W1 by L1, you could be using a scaled version of it, that is M times W by L and M times W1 by L1 over there. Then the GM of this would be equal to M times 1 over R. Okay. And this differential pair will be operating with some VCM. So, what you do is you use whatever biasing arrangement that is possible, like for instance you can simply use a diode connected transistor, 1 or 2 of them. Okay. Basically the point is to bias this at approximately the VCM of the differential pair that you are using, so that the differential pair whose GM you are locking to 1 over R and the differential pair that you are using are operating at around the same condition. Okay. That is how you can come up with bias currents which will bias the transistor such that their GM is constant with temperature, and this is very important in certain applications, many times in filters and so on, where you would like the characteristics to not vary with temperature. We will continue on these things and also see how to generate voltage references in the next lecture. Thank you.